next we have the closed pack structure. That means in this part we are going to learn about the packing in solid, how the particles, that is atom, molecule or ions, are arranged in a solid. We are talking about the crystalline solid, and as I said that in crystalline solid all the particles are arranged in a definite order. There is a fixed arrangement of the particles. The particles are arranged in a such a way that on joining it we get a simple cubic cell or body centered cubic cell or face centered, or we get a tetragonal structure or rhombohedral or monoclinic or triclinic. So ultimately here we are going to learn that how the particles are arranged, how those atom, molecule or ions are arranged, so that we get cubic or tetragonal or rhombic structure or other types of crystal system or the unit cell. So it's a closed pack structure. Here mainly we are talking about the cubic structure, means we are going to learn that how the particles are arranged so that we get a cubic crystal system. As the cubic, we are talking only about the cubic crystal system in this part. The reason because the cubic is the simplest one and the tetragonal and orthorhombic is little bit complicated. So closed pack structure. For a cubic, we have three types, that is a simple, body centered and face centered. So in this part, we are going to learn that how the spheres will be arranged so that we will get a simple cubic cell or joining those spheres. Spheres are nothing but the atom or molecule which is in a spherical form. How the particles are arranged so that on joining them we will get a body centered cubic cell. How the particles are arranged so that on joining we will get face centered cubic cell. So let's see. The first one is So in a solid we have actually the three-dimensional packing. All the particles are arranged in a three-dimensional way. But to understand that three-dimensional packing, we should know that one-dimensional and two-dimensional arrangement. So let's start with the first one, that is a one-dimensional packing. This one-dimensional packing is also known as linear packing in solid. So here in this part we are talking about the arrangement of particles. One-dimensional packing. In one-dimensional packing, as you can see that here all the particles are arranged in a straight line. After that one particle there is other, then other and other. So all the particles are arranged in a straight line, and all the particles are arranged in a straight line. That's why it is called as a one-dimensional packing, also known as linear packing, because if I'm joining the centers of every particle, then simply you can say that a single line will be obtained, and hence since on joining the centers we are getting a single line, so linear packing. Now the very important thing in the packing part is the coordination number. In an exam, the coordination number is asked for the different types of packing. So I just wanted to know the coordination number of the particles in this case, in a one-dimensional packing. So coordination number, that is a number of surrounding particles which are directly contact with the given particle. Suppose if I wanted to know the coordination number of any particle, then just check out that how many different particles are directly contact with the same particle. So suppose there is any desired particle, I am representing in a diagram by D. You can see that D is surrounded by the two different particles. The one is present on the left hand side, one is present on the right hand side. So here I can say that there are inner coordination number, means every particle is touching to the two other particles, and hence the coordination number is 2. If I am considering the last particle also, the last particle here on this side we have 1, and on that side again which is not drawn, means every particle, whether it is on the last or in the center, it is surrounded by two particles. Then second one, after one-dimensional packing, we have two-dimensional packing. Which is also known as planar packing, because here we are getting a plane after joining or after arranging all the particles. As I said, we are doing one-dimensional and two-dimensional just to understand the three-dimensional packing properly. Otherwise, in a solid, there is only three-dimensional packing. So, planar packing. Now, in this case, we have two types of arrangement, or the two different types of packing. The one is known as AAA type packing, which is also known as square closed packing. Second one is AB type packing. Which is also known as hexagonal close packing. Now let's see what is that AB and AB type of packing. Here we have the one-dimensional packing. One-dimensional packing means where all the spheres are arranged in a first line, in a one row. Now, when the same one-dimensional rows are kept one below each other, here currently we are having only the length, but when the second row, third row, fourth row is kept one below each other, then you can see that second row is kept, then third row, then fourth row, and then fifth row. Then we are getting a length as well as width. Now, depending on how the second row is kept, on that basis here we have the two different types of packing, that is AAA type and AB type packing. The second row, now how the second row is kept. Now in this diagram you can say that the second row is placed exactly below the particles of the first row, that is the first row particle and the second row particle are exactly below to each other. Second row and third row particles are exactly below to each other. Third row, fourth row are exactly below to each other. Now in the case of this arrangement, you can see that the particles which are present in a first layer. Someone asked me that how the particles are arranged in a first row. I said let the particle arrangement is A type. So in a second row also the arrangement, since the second row is also having the same arrangement, how to know whether the arrangement is same or not? If the second row particle, since the second row particles, atoms or the spheres are exactly below the first row spheres, that's so we can say that the second row particle have the same arrangement like the first row. Third row spheres we can say that exactly below the second row. Fourth row are exactly below the third row, second row, first row. Means I can say that all rows particles are arranged in the same manner. So if the first row is called A arrangement, then second, third, fourth, everyone will be called as A type of arrangement. So all are A type packing. Now, in the case of this A type packing, what will be the coordination number? So to get that coordination number, you consider any desired atom, any atom you consider, and just check out that how many surrounding atoms are there. So in this case, suppose I consider a D, that is a desired atom, and just how many surrounding atoms are there, then here I can say that 1, 2, 3, 4, there are total 4 atoms. So here coordination number is going to be, in this case, the coordination number for A type packing is 4. This is also known as square close packing. Now why it is called as a square close packing? The simple reason that when we join the centers of those neighboring particle, that means here we have 1, 2, 3, 4 spheres for the 4 surrounding spheres. When we join the centers of those 4 surrounding spheres, we get a square, and hence it is called as a square close packing. Now let's talk about the AB type of packing. AB type of packing, here I can say AB type packing or hexagonal close packing. Now AB, A and B, here A means all the layers were having the same arrangement. AB, that means the first layer arrangement is A. I'm giving the second layer arrangement, I'm calling it as a B arrangement. B arrangement means it's not like the second row is not exactly like the first row. Now this is the diagram, or this is the arrangement for the AB type of packing. Now in this AB type packing, you can see that the first layer, the second layer, now I'm keeping the second layer. In case of second layer, you can see that second layer is not exactly below the first layer. Instead, it is present in the depth of the first layer. The crest of the sphere, that is the upper part of the second row sphere, is placed in the depth of the first row. Similarly, if you have, so first row arrangement is called A arrangement. The secondary arrangement is not exactly like the first row arrangement. The reason, because particles are not exactly below. So the second row arrangement will be something different. I call it as a B. Then I kept the third row. Third row particles are again exactly below, exactly in the depth of the second row particle. Fourth row particles are exactly in the depth of the third row particle. So here all the next row particles are placed in the depth of the previous row particles. Now in the case of this, you can say that first row and the third row particle, first row and third row particle are exactly one below each other. If I'm removing the second row, you can see that the first and third row particles will be exactly one above each other. That means the first row particle and the third row particles are arranged in the same arrangement. So if I'm calling first row as A, the second row is going to be B. Then again first row is A because the arrangement is same. Again the next row is B. So I can say that here we are having AB type packing. AB type packing means every alternate rows are having the same arrangement, but the two consecutive rows are not having the same arrangement. Now in this case, I just wanted to know the coordination number. So to get the coordination number, you consider any atom, again any sphere. Let I'm labeling as a D. So that desired every spheres, you can see that it is surrounded by the 6 spheres. 1, 2, 3, 4, 5 and 6. So there are 6 spheres around every sphere. So coordination number is equal to, I can say, 6. Now what is called hexagonal close packing? The reason for calling it as a square close packing is the same the reason which we use for calling it as a hexagonal close packing. When we join the centers of those neighboring 6 particles, 1, 2, 3, 4, 5, 6 particles, when it is joined, you can see that here the center, on joining the centers, we are getting a hexagon, and hence it is called as hexagonal close packing. Since on joining the centers of the neighboring particle, we are getting a hexagon, that's why it is called as hexagonal close packing. So this is about the two-dimensional close packing. As I said, we have two types, AA type and AB type. AA type means where all the rows, all the particles present in each and every rows are arranged in the same manner. While in case of AB, the arrangement of the particles are in a different row, they are different. But AB, that is first row and third row, have the same arrangement. Second row and the fourth row have the same arrangement. Similarly, after B, that is if I am moving to the fifth row, the arrangement is going to be same. Sixth row will have the arrangement like the fourth row. The next is a three-dimensional packing. After one and two-dimensional, three-dimensional packing. As I said that in a solid, generally the three-dimensional packing is only present. So now let's see how the particles are actually present in a solid. Now three-dimensional packing means in a one-dimensional we saw that the particles were present only in a single row. But when the same particles, same rows are kept one below each other, then we got a two-dimensional packing. That means in a two-dimensional packing we get a layer. One layer we got, one plane we got. Now in three-dimensional what happened? On one above each other, the one plane, above this the second plane is kept, then third plane is kept, then fourth plane is kept, or fourth layer, second layer, third layer is kept, keeps on. We keep second, third and fourth layer on in case of three-dimensional packing. So here depending on how the layers are kept one above each other, we have three different types of three-dimensional packing. There are three different types of three-dimensional packing. The first one is called as AAA type three-dimensional packing. The next is AB type three-dimensional packing, and the third is ABC type three-dimensional packing. In two-dimensional as well as in three-dimensional, here also we have AAA type packing. So let's start with the first one, that is AAA type packing, but now it is three-dimensional AAA type packing, which is also known as, here in this case when it is a three-dimensional, then it is known as simple cube packing. So AAA type packing, or it is also known as I said, simple cube packing or simple cubic packing. Okay, now let's see how the particles are arranged in this case. Now this is arranged, or this is from the two-dimensional AA type layer. It is formed from two-dimensional AAA type layer, that is square close pack layer. If you want this packing, then this is start with the two-dimensional square close pack layer. Square close pack layer means where all the particles present in a different layer was arranged in the same manner. So in a diagram or in animation, you can see that we have the first layer of first layer, and this layers appears like a square close pack layer, that is two-dimensional layer. Now I want the three-dimensional packing. So what we are doing now, the next step is keep the another layer on it. So when the second layer of the ball is kept, now second layer can be kept, can be placed either on the ball of the first layer, or it may be placed in the voids which are present between the balls. But since, as I said, the name is AAA type, that means the arrangement is going to be same. Now here A, in the case of two-dimensional, A stand for the arrangement of particle in a row. But now in this case, A stand for the arrangement of a particle in a layer. So here now A stand for the arrangement of all the particle in a same layer. So this is the first layer we have. When the second layer is kept, the arrangement of the second layer particle is exactly like the first layer. Exactly like the first layer, that means the second layer particle is going to be exactly on the particles of the first row. Then similarly, third layer particle will be exactly like on the particle of the second row. Then fourth layer, fifth layer, and so on. So ultimately we will get a cube, we will get a structure, and the way this diagram is appearing, I can say that in a solid, the same types, in the same manner the particles are arranged, that is atom or molecules are arranged in a solid. Now this is called AAA type packing. The reason of calling it as a AAA type, because the different layers arrangement is, the arrangement of a particle in all the layers are same. Now I just, again in this case also, I just wanted to know the coordination number. The coordination number, that is a number of touching sphere. So you consider any sphere and just think that how many touching spheres are there. So I can say that I'm considering the one particle from any one layer. So you consider any one particle. So one particle, this is I'm labeling it as a D, which is touching to the 4 particle of the same layer, 1, 2, 3, 4. And there is a one particle which is exactly below to this sphere from the lower layer. That means from this particle, desired atom is touching to a particle from the lower layer. From lower layer there is only one particle. Plus there is a one more particle which is touching to it from the upper layer also. From upper layer also there will be a one particle. So I can say that here the coordination number is 6. Coordination number 6, which can be written like 1 from the upper layer, 4 from the same layer, and 1 from the lower layer, and hence the coordination number is 6 for this. The next, after the coordination number, we are calling it as a simple cubic packing. Why it is called as a simple cubic packing? Simply I will say you start joining the particles of the different layer, the centers of the particle which are touching to each other from different layer. So I'm considering the first 2 layers. When we join the centers of their particles, you can see that on joining the centers, 4 from the upper layer, 4 from the lower layer, and when we join we are getting a simple cube, and that's why it is called as a simple cube, where the particles are present only on the corner, and that's why we called it as a simple cubic packing. It means if I'm saying that there is a particular solid which contains simple unit cell, that means in that particular solid all the atoms will be arranged in this manner, and if the particles are arranged in this manner, then only we will get a simple unit cell, simple cubic cell, that is a particle present on a corner, as well as all the edges, and all the edges are equal and all the angles are 90 degrees. So this is about the first type of the 3-dimensional packing, that is AAA type packing, or also known as simple cubic packing, with the coordination number 6.